All right, so this is CS50, and this is week 8 already. My thanks to Adam on today, this happy Halloween. In the coming moments, we're going to learn all about how the internet itself works, which of course is a technology that we all use every day, probably using in some form right now. But we'll see that if you start to understand some of the underlying building blocks that power the internet itself, we can actually start to build interesting things on top of it. And a lot of the apps, the websites that you all use every day should become all the more familiar, things that you yourselves can create. And honestly, when things go wrong, you'll have all the more of a mental model for how things work or are not in fact working, so that you can ultimately diagnose all the more issues yourselves. So if we take a look at the internet in the early days, it pretty much was just this. This happens to be, of course, the geography of the United States, and just some of the first points on the internet were these here. This was so-called ARPANET back in 1969, and indeed the internet had its origins here in the United States with just a few computers interconnected somehow initially. That, of course, began to grow over time such that we eventually had the West Coast connected to the East Coast, and nowadays what you can think of, these dots on the screen as representing, are these things called routers, sort of computers, or really servers, that somehow have wires or maybe wireless connections between them that allow data to flow from point A to B to C. And then this, of course, has been now magnified across the entire globe and even above ground as well, so that we can connect all the more readily to systems anywhere. Now, in order to route the data from one router to another, we need to somehow make routing decisions. And this is the kind of thing that the internet service providers, the ISPs of the world, just handle for us. You and I plug our Macs, our PCs into the network here at Harvard, or equivalently at Yale, or we somehow get online via Wi-Fi or cellular technology. And then some of these larger entities, these bigger companies or countries, handle most of the data getting from point A to point B. And if you think about what these routers represent, they're indeed just servers somehow interconnected, not unlike this grid of tiles here, for instance, back in the Zoom days. And in fact, here we have, I claim, a grid of routers implemented here by the course's teaching fellows and course assistants and TAs. And if the goal at hand, for instance, is for Phyllis to route some piece of information, maybe it's an email, maybe it's a request for a web page in the bottom right-hand corner, all the way up to, say, Brian here in the top left-hand corner, suffice it to say, each of these tiles represents a router, a server that can move the data back, forth, left, and right. That packet of information, so to speak, from Phyllis to Brian could take any number of different possible routes, up, down, left, right, to go from the one corner to another. So let me go ahead and hit play on this video here, wherein the teaching fellows play this same role. All right, so in this particular case, the data was routed pretty straightforwardly up and then to the left. But suppose that one or more of the staff were a bit busy. Maybe one of the routers is congested. That is to say, just get way more envelopes at a moment in time than it can handle. Thankfully, the design of the internet is such that there's often multiple ways that data can get from point A to point B, maybe going through point C or point D instead. And so there's a resilience there, even as some of these servers themselves might go down. So allow me to propose that we use the same grid of routers now to route the data. Whoops. Allow me to route the data in a slightly different way this time. So success. You'll see perhaps later just how many takes it took us to actually get that routing right. But it does, in fact, manifest that you can travel different paths in order to get the data from point A to point B. So as we talk about routers, as you think of the internet, I mean, think of those humans as just representing these routers, points A to P and everywhere in between. Now, how did the teaching staff know to route that packet up and then down or left and right in order to get to the destination? Well, all of them were programmed, so to speak, to understand protocols. It's called TCP and IP, otherwise known together typically as TCP/IP. And you've probably seen these acronyms at some point in the real world, on the internet, on some kind of documentation, a text, even if you haven't really thought hard about it. But IP is certainly the more common of the two, perhaps, in common culture. So what does TCP and IP do for us? Well, really two primary things. Any computer or any teaching staff member who understands TCP/IP knows how to get data from point A to point B. But how? Well, let's break down what that problem to be solved is. IP, otherwise known as Internet Protocol, is a protocol that computers speak that allow them to know how to address computers on the internet. And a protocol is just a set of conventions that computers adhere to. So someone wrote code that probably has a whole lot of conditionals that tells the computer what to do if something happens. Like, if I receive a packet, then send it to the next server, or something like that. In the human world, we have protocols too. In healthier times, it was quite common to sort of extend your hand to another human in order to greet them. And if they're following human protocol, they would presumably grab your hand and shake it, at least in a culture like this one here on campus. And now that is a human protocol in that someone initiates it, someone responds to it, and you both sort of know what to do. You're programmed to know what to do. So same idea with Internet Protocol. Computers just know what to do when they've been programmed to do so. So what does this mean? IP decides that every computer in the world will have a unique address, just like the Science Center around the corner might have a unique address of 1 Oxford Street, Cambridge, Massachusetts, 02138 USA. IP dictates that every computer on the internet have a unique address of this form. And this, too, is probably something you've seen in the real world, even if you haven't thought too hard about it. It's a number in what's called dotted decimal notation, which means it's a decimal number, dot something, dot something, dot something. So 4 digits separated by convention by decimal points, although there are newer and bigger versions of the same. And these so-called IP addresses that might be as simple as 1.2.3.4 uniquely identify a computer on the internet. The numbers have to range from 0 to 255 each. And that's a bit of a hint just as you start to think more computationally. If each of these is a number from 0 to 255, how many bits does that suggest each number is using? Feel free to shout it out. How many bits gives us 256 total possibilities? So 8 bits. That should just be sort of a heuristic in your mind. Anytime you hear something that's in the range of 0 to 255 or 256 values total, think back to week 0, which gives us 8 bits plus another 8 bits, another 8 bits, and another 8 bits, which is to say an IP address typically is 32 bits in total. Now, if we do another bit of quick mental math or think back to week 0, if every IP address is 32 bits, how many computers can we have on the internet at once, give or take? Roughly 4 billion is the ballpark. And we don't need to be super precise for discussion's sake, but roughly 4 billion is how high you can count, assuming no negative numbers, if you have 32 bits in total. Now, that's not terribly many numbers of addresses, especially considering the number of humans in the world, the number of us that do have laptops or desktops or devices more generally, phones in our pockets and the like. So let me just stipulate for today's purposes that there's even a newer and improved version of IP, otherwise known as version 6. This is version 4, but still super popular. Version 6 uses 128 bits, which is a huge number of possible permutations. I dare say I can't even pronounce that number. It's so big. So there are ways around even this limitation already. So every computer has an address like this. What does that really mean? Well, suppose that I was Phyllis in the story told visually earlier, and I want to send a message to Brian. Well, both Phyllis and Brian have IP addresses. And suppose that Brian's IP address happens to be 1.2.3.4 in that top left-hand corner. Well, Phyllis's Mac or PC or phone would essentially do the equivalent on this human envelope by writing the to address in the middle of the envelope, as is our human convention, like this. So this is an envelope, a piece of information, an email, a text message, whatever, destined for Brian. And so she would have her computer put Brian's IP address in the middle. Her IP address is maybe 5.6.7.8. So just like our human convention, I might write 5.6.7.8 at the top of the envelope. 5, 6, 7, 8, thereby indicating what the return address is. And this is helpful because if Brian's computer needs to acknowledge receipt, if he needs to reply in some form, this way the envelope has all the information we need. But in the real world, servers do a lot of things nowadays, not just email, but maybe chat, maybe video conferencing, maybe any number of other services as well. And so it turns out that an address alone might not be sufficient, because how does Brian's computer know when he opens the envelope, so to speak, that this should be interpreted as an email, or interpreted as a chat message, or interpreted as like a video attachment that Phyllis has sent? Well, we need some other mechanism, some other hint on this envelope to distinguish one type of internet service from another. And so that's where the other acronym in TCP/IP comes in, which is TCP. So this stands for Transmission Control Protocol, which is just a different set of conventions that computers adhere to in order to solve a couple of different problems. One is this problem of distinguishing one type of service from another. Now, what does that mean? Well, humans decades ago decided, as they started inventing all of these various internet services, the web being the first one, how they might, or the web now being one of the most popular ones, they decided to assign different services that can be used on the internet unique numbers. And so two of the most common are these. 80 is the number that a bunch of humans decided years ago will represent what you and I know as HTTP. And we'll talk more technically in a bit about what HTTP is, but obviously it's the thing that's in the beginning of every URL nowadays. Or HTTPS, which of course has the S added to it, and that has its own unique number. And for now, the S just means secure. One is encrypted or scrambled somehow for privacy's sake, and the other is unencrypted. It's a little more vulnerable to interception. So these two numbers are what the world decided when implementing TCP shall uniquely identify those services. So what does this mean? Well, this means that if Brian's computer in the story from before is hosting not like an email server, but maybe he has a website, and Phyllis is requesting Brian's homepage or something like that, she would have her Mac or PC or phone not only write Brian's IP address in the middle of the envelope, but also the number, otherwise known as a port number, that she wants this envelope to be routed to. Now, 80 would be insecure nowadays. HTTP:// is sort of passé, and we almost always see HTTPS:// now. So I'm just going to go with best practice, and I'm going to add a colon and then the number 443 at the end of Brian's IP address. So now I have an IP address for Brian, the port number for the service that this is relevant to, and I'm not going to bother writing it, but it turns out that Phyllis's computer would also choose a port number, maybe a random port number, so that Brian can conversely reply. And then the computer can know which response is coming back for which request. But the most important one is this one in the to field, whereby this distinguishes this from like an email, a chat message, a video conference session, or a Zoom or whatnot from anything else happening on Brian's computer at the same time. So all this time, if you've seen these terms TCP and IP, those are really two of the most important things that they do. But TCP does one other thing that's super useful too. It turns out that it's super common nowadays, especially, to transmit a lot of media on the internet, whether it's an image or maybe it's a movie file. And it would be a little obnoxious, to say the least, if you're downloading a really big file meant that no one else in your dorm room or your household could actually download anything until you're actually done. So of course, multiple people nowadays can be on the internet at once, even if all of the connections are a little slower. But like one person's usage does not block someone else's. Now, how does this work? Well, TCP in conjunction with IP can also allow you to take like a really big image of a cat, which is the internet, of course, is filled with, and take a big image of a cat or a big video file of a cat and fragment it into multiple pieces. So I'm just going to sort of roughly tear it down the middle and then maybe tear it down the middle again. So now it's 4 different fragments. And I'm sorry, but the computer will be reassembling these for us. And what Phyllis's computer could do now, if she's like uploading this picture of a cat to Brian's web server, well, she could put one fragment in this envelope and then have 3 separate envelopes for the other 3 fragments. And what she could then do on the outside of this envelope is just kind of number them somehow. And in fact, this is something else that TCP and IP together would do for us. This first envelope now might say something like 1 out of 4 in the memo field, so to speak, of the metaphorical envelope here. Now, this should be enough information, because now if Brian gets all 4 of these envelopes, he presumably knows how to reassemble the picture of the cat in order, top to bottom, left to right. But more importantly, suppose that one of the routers, one of the TFs in the video, is sort of distracted and they sort of drop one of the packets. And that's a metaphor actually in practice for when a router gets really busy, it's got way too much data coming in, it might metaphorically drop packets. What does that mean in practice? I mean, it literally just ignores the zeros and ones. It doesn't save them to its memory because there's just no room left. So it's equivalent to sort of dropping the packet. So suppose now that Brian gets 1 of 4, 3 of 4, and 4 of 4. What can his computer infer now? after receiving those 3 packets, 1 of 4, 3 of 4, and 4 of 4, what's the use there? Yeah, I think you're signaling with your fingers. Which one can I call on you? Yeah, so he's missing 2 out of 4, the second of the packets. And this is useful now because you could imagine he can send some message back to Phyllis saying, hey, please retransmit number 2 of 4 without having to re-download the entirety of the cat. So there's an efficiency there as well. So TCP/IP allows data really to go from point A to point B while solving a bunch of these problems along the way. So nowadays, if you ever see mention on your Mac or PC of your so-called IP address, that is the sort of problem that's being solved. Questions now on these protocols, these conventions called TCP and IP. That's the extent to which we'll need to understand them. Won't have to implement them per se. We'll just take them hereafter for granted. Any questions that you've ever been wondering about your home network? Yeah? A really good question. How does TCP know that a user got a message? Another aspect, another feature of TCP is that Brian's computer, by design of this protocol, will also acknowledge the packets that he's received. And it will do it efficiently. If Brian receives all 4 packets in a pretty narrow window of time, his computer will send to Phyllis's computer a quick message saying, essentially received all 4. Otherwise, he'll say the opposite, which is that I'm missing, for instance, 2 out of 4. And that just ensures ultimately that all of the data is indeed arrived so that you're not missing like a quadrant of the cat in question. All right.